Okay, today we're going to talk about magnetism. Before I get started, just a quick note. We have two groups that have identified the topic they're going to do for their project. One was on metal detecting, making a metal detector, which is using magnetic inductance. And the other one is inductive charging. Both of them are dealing with magnetic inductance, but in very different ways. So it's acceptable. They're not the same thing. So those are two topics that are taken. I hope to hear 3 additional ones soon. I did accurately portray that, did I not? 2 groups.
Yeah.
Okay. Well, actually, everybody who said yes was from the inductive charging group. Today we're going to start with the ideas that are necessary for those 2 projects. Magnetism. Now, both of those projects are actually dealing with electromagnetism. We've already studied electricity. Now we're going to study magnetism, and then finally we're going to see how the 2 interact. And that's what they're doing with their project, is studying how they interact. So first, magnetism. As the story goes, in Magnesia, which is somewhere over in, I don't know, the area of Turkey or something like that, if I remember geography right, a shepherd had, and this is a story, it's probably untrue, had a metal-tipped staff, and he noticed that staff stuck to some rocks. And so people started studying this, and they called it magnetism. I actually was fool enough to go buy a book about the history of magnetism. It turned out it wasn't written from a physics perspective. It, talks about very interesting magical properties people believe that magnetism had. But basically, the essence of what was first known about magnets is I have a magnet, and I can bring it up here, and look, it attracts one side and it repels the other. And so just like with electric charge, they quickly determined that there are 2 types of charges for magnetism. But furthermore, they noticed if you look at this, it will eventually stop. So the red painted side is pointing to the back of the classroom, and the blue painted side is pointing to the front of the classroom. And so they said, wow, that's really weird. The red one is seeking the Earth's north pole. And so they called it the north-seeking pole. So now we're calling our charges poles with magnetism. So we have the north pole, and the other one is pointing toward the Earth's south pole, so it's the south-seeking pole, and we call it the south pole. So magnets are identified with 2 charges, north and south. Now, one thing that also has been experimentally determined is that you never find a north pole without a south pole. They always come together. So the total charge of anything is always, the total magnetic charge is always 0. You have exactly as much north as you have south. So we say there's no such thing as a magnetic monopole, having just north or just south. You always have the 2 together. And so with more experimentation, you discover things like this here is magnetized, so it's going to seek north, right? I'm going to take this and I'm going to put it in a really strong magnetic field. So I have this here that's going to make a strong magnetic field. And I'm going to put it in some randomly chosen way, not so random, and turn on the strong magnetic field. You might have seen it kind of jumped when I turned on the magnetic field because, of course, strong magnetic field made it attract. Now I put this back on here, and ruh-roh. Anybody? Well, Gila can see. What happened when I did that, Gila?
It doesn't point that way anymore. Or it's moving.
And in fact, when it stops, I started it with north pointing north. I just reversed my compass. Now the one that is painted blue is seeking north. How in the world was that possible? I'm going to fix it now. How in the world was that possible? Any ideas?
electrons to the other side, or well, move the charge towards the other side of it.
Okay, so I pulled the charge toward it. It's actually not a charge answer. Right, we haven't studied magnetism, so that's a great stab at it. But it's not a charge answer. Jonathan?
You realigned the atoms so that the electrons were working.
Okay, I realigned the atoms. It turns out the magnetism here is based on the magnetic dipole moments of electrons, protons, neutrons. How many people knew that neutrons were magnetic? They are. They have a magnetic dipole moment. That means they behave like little bar magnets, even though their charge is neutral. Electrons also behave like little bar magnets. They have a dipole moment. Protons also behave like little bar magnets. They have a dipole moment. Electrons orbiting the nucleus also create a magnetic field. So in an atom, you have lots of things to create different magnetic fields. Now, I use the word field. I'm going to come to that in just a moment. But those things will give me different magnetic properties. So when we talk about magnetic properties, we're really talking about things that go down to the atomic level that's causing the magnetic properties. And so I did something here that Jonathan identified correctly. I took the little magnetic dipole moments in here, and I realigned things. When I put a strong magnetic field, I was able to realign them. So now let's get started with my general lecture. Magnets make a force, as we saw, right? It wouldn't be north-seeking if it didn't make a force. And so, because it makes a force, we talk about magnetic fields to help us calculate the force, just like we talked about electric fields to help us calculate the electric field, or gravitational fields to help us calculate the gravitational force. So this picture here on the left is showing reasonably close to the Earth what the Earth's magnetic field lines look like. So we have the first thing that you may note is odd. You can see here this is Mexico right there. The USA right there. So which side is north in this picture? The which side?
The upside down side. The bottom side.
Well, no, the USA is in the northern hemisphere.
Oh, I thought you were talking about the magnet.
So, okay, yes, that's what I'm getting to. So this here is the north geographic pole. And so a magnet's north seeking will point that direction. But what was discovered reasonably quickly was, just like with charge, opposites attract. So that means a north magnetic pole is attracted to a south magnetic pole. And since we named this red side north, it's being attracted toward south. And so because of the way they define magnetic poles as a north-seeking pole we call north, then when they discover the opposites attract, that means that the Earth's north geographic pole is, and this is what Jordan has been noticing, the south magnetic pole. How convenient. Now, will it always be this way? No, thank goodness. Approximately every 200,000 years, the Earth's poles flip. It happens in the sun every roughly 11 years. So, how long has it been since the Earth's magnetic poles have flipped? About 1 million years or so. We're long overdue for a flip. Doesn't mean it's going to happen in our lifetime. If it happens, it probably will take more than our lifetime to actually go through the sequence. Question?
How does it flip?
How does it flip? Going way ahead of the lecture then, I talked about in the atom we have magnetism due to the electrons behaving like little bar magnets, the protons behaving like little bar magnets, the neutrons behaving like little bar magnets, and the electrons in their orbits creating a magnetic field. It's that part of the electrons in their orbits that becomes relevant. We believe, no one's been there to investigate, but we believe at the center of the Earth there is a molten core that is liquid material. And that liquid material is swirling because the Earth is rotating. based on based on the production of elements in stars as they're dying, stars can produce elements up to okay, I have to back up. Big Bang Theory. During the Big Bang, the theory is that energy formed protons and neutrons. And then protons and neutrons collided together and formed things like hydrogen 2, hydrogen 3, helium 3, and helium 4, just by adding together. But there is no stable element with 5 nucleons in it. And because of that, and the probabilities of having something with 2 colliding with something with 3, or with 4, or something with 3 with 3, they believe that during the Big Bang, no element larger than helium was created with any significant fraction. It also turns out that 8 is another stopper. I think it's 8. There's no stable element with 8 nucleons. So it's another stopper. So basically only hydrogen, helium in the Big Bang. Any element above that, according to scientific theories, can only be created in a star. A star like our sun will produce, right now it's producing helium. When it gets into its giant stage, it will start producing copper and some oxygen. And that's where our sun will end. It won't make any elements bigger than oxygen. But in the death, I know I'm going through a whole long description for your answer. In the death of a massive star, it can fuse things up until it produces iron. But that's the largest element that can be produced in a dying star, because nuclear fusion, you have to, in all things, go to a lower energy state when you're done, or it's not going to naturally occur. Nuclear fusion is combining smaller nuclei to make a bigger nucleus and release energy. But it turns out iron and nickel are the most strongly bound nuclei. So that means it's the lowest potential energy per nucleon to make those two. So fusion can occur naturally up to iron and nickel and not beyond there. So fusion, naturally occurring fusion, is not going to make silver or gold. So during the death of large stars, you're producing elements up to iron. During the final moment of a large star, it undergoes a supernova, and in that supernova, that's where you create any elements that are larger than iron. And so those elements larger than iron are much rarer than the elements from iron to oxygen, and then going from oxygen, they become much more common in the universe. So all of this said, scientific theory then says that the most common dense element on Earth should be iron. All of that to say the most common dense element on Earth should be iron, and so we believe that the core of the Earth is primarily iron, maybe some nickel, because differentiation, that is, more dense material sinking through the Earth, ends up with a higher proportion of those in the center. So we believe we have a conducting metal in liquid form swirling around, and that will create a magnetic field. So all of that, that's what we call the geodynamo. And so this geodynamo, you actually need 3 things. It needs to be a liquid, it needs to be a liquid that's swirling, it needs to be a conductor, it needs to have convection. You guys remember what convection is?
Because the flow of material.
Okay, heat causes material to flow. So you have hot material floats up, cold material sinks down. You have to have all those things to make a magnetic field. These things become interesting in astronomy because you look at something like Venus. Venus has no magnetic field. So it's got to have one of those 3 things missing. Well, by every theory, it should have a molten core. Even though it's rotating backward really, really slowly, models show it should be fast enough that it should be making a magnetic field. So the conclusion is, it must not have a big enough temperature difference to have convection. Whereas you look at Mercury that has a very, very tiny magnetic field, conclusion there is that it's nearly frozen. So it doesn't have much motion. Okay, all of this said, why would our magnetic field reverse? We look at the sun to help us understand that. Because the sun has a heliodynamo, if you will, and the sun is liquid metallic hydrogen. Was there somebody here who's talking about the liquid metallic hydrogen? No, must be another class. Okay, liquid metallic hydrogen is what we believe is swirling in the sun to make its magnetic field. And the sun makes a much stronger magnetic field. And magnetic field lines, these lines like we see here, interfere with each other. You have in the sun what we call differential rotation. The sun is not a solid object, right? It's a fluid. And it turns out that the sun rotates faster at its equator than it does at the poles. So if you're in a boat, in a boat floating on the sun, it would take you longer to go around the sun once if you're just floating close to the pole than it would the equator. Well, that drags the magnetic field lines with it. The magnetic field lines start to get tangled up. They start coming out of the sun, going back in. So we see sunstorms where the strong magnetic fields suppress the convection of the sun. And eventually those magnetic field lines are starting to tangle on each other, and the forces of the magnetic field lines interacting causes the swirling in the center to get disrupted and to basically control the lead on the sun. It starts over with the magnetic field going the opposite direction. Pretty bizarre process. So we take that, we can see the sun changing, every roughly 11 years. So we can study it a lot more than the Earth. And then we take that information, we say, okay, we think this is going on the Earth, but at a much smaller level. And the Earth is not nearly as predictable because it's a much smaller level. We can actually make measurements looking in the ocean floors. Sailors notice when they're sailing across the ocean that their compasses would do wacky things and not point north. And so scientists, of course, we know the scientific method by now. You observe something interesting, you come up with a hypothesis to try to explain it, and then you start doing tests of it. And so the scientists went out there and tested, and they found that the ocean floors have regions with different magnetic alignments. And so their conclusion is you have rift zones in the middle of the ocean floors, like, see this crack here? You have cracks like that in the Earth's crust. And molten magma pushes up between those, kind of like Samson pushing those pillars apart. It's pushing the plates apart. So that's what the rift zones are, places where magma is coming up and pushing the plates apart. Well, that magma is molten rock, and it has magnetic materials in it. And so those magnetic materials in molten material will just align with whatever magnets around them. But then when they freeze, they get stuck that way. And so you can record, the ocean floors record the direction of the Earth's magnetic field to tell us about its reversals. I know, I used up a quarter of the class period to answer that question. But it's good stuff that deals with what we're learning. Go ahead. Oh, I thought you said, so where are you leading with this? If we were to look at a picture of the Earth's magnetic field from further back, it wouldn't look nice and uniform like this. And that's because of the sun. The sun is shooting out lots of positively charged material at us. We call it the solar wind. And that solar wind comes in and it compresses the magnetic field lines on the side close to the sun and elongates them on the other side. So it's not perfectly uniform. So getting back to this, the magnetic field lines. Magnetic field lines are lines of force, lines to help us calculate force. But the weird thing is, the magnetic field lines always come out of north. So they're coming out of north, and they always go into south. Okay, my colors are the wrong colors here. Well, so they go into south and come out of north. If I put a magnet in a magnetic field, such as this compass, there will be a torque because this north is going to be attracted to the south magnetic pole. The south is attracted to the north magnetic pole. So there's going to be a torque to make it rotate. Because it has a net magnetic charge of 0, we mostly notice just that torque. So if I take a magnet and I put it out here, so I'll put a magnet here, it's going to have a torque to make it quickly align, so it will rotate. So it's pointing like this, with north there and south here. Now, when we calculate magnetic force, we're never going to actually calculate the force between two magnets in this class. It's pretty complicated. Instead, we're going to calculate the force on charge in a magnetic field. So all we're going to do in terms of force is to know that opposites attract, and there will be a torque placed to make the magnetic fields come out of north and go into south. Notice one last thing. The magnetic field lines continue on through the magnet. It's not like electric field lines where in a stable situation there's no electric field inside. For magnets, the magnetic field lines go through. So all of these magnetic field lines are continuous. They never end. They do circles or loops. So that's a difference between electric fields and magnetic fields. Magnetic fields don't end. Why? Because there's no magnetic monopole. We actually, for magnetism, we have Gauss's law for magnetism. Gauss's law said that the charge enclosed told me about the magnetic flux for the surface that's enclosing it. Well, for magnetism, by definition, what is the charge enclosed by a closed surface? It's always zero because there's no magnetic monopole. So we still have Gauss's law for magnetism, but it just says on any closed surface, the magnetic flux has to be zero because the charge enclosed is zero. Okay, this other picture, one to get us excited. What is this? Northern Lights. Anybody ever seen Northern Lights? None of you? Okay, couple. So, perfect, green on green. I don't remember how many E's are in Borealis, so I'm going with one. Aurora Borealis, the Northern Lights. We also have Aurora Australis. I think it's Australis, not Australis. The Southern Lights. So we have the Northern and Southern Lights. Why would that come up in this chapter heading? It must have something to do with the magnetic field. Gabriel?
It happens when electrons ionize gas in the atmosphere, doesn't it?
It does?
And so,
Well, it's actually protons, but
but you have cosmic rays that introduce magnetic fields.
yep.
So it would be the sun from the sun from the
Okay. The cosmic wind from the sun, the charged particles flying out from the sun loses tons like every second. But it has so much mass, it doesn't matter. And so that mass comes and hits us, and the force between a magnet and charge, and we'll learn about this force next class period, is unique in that it will make the charge deflect away from the Earth if it's coming where I showed with my two arrows here. It'll deflect away. So the Earth's magnetic field protects us from the cosmic radiation. We receive far less radiation in the form of charged particles flying through our bodies than we would without the Earth's magnetic field. But if it comes up here, it spirals around the magnetic field lines. And so charged particles do come into the atmosphere closer to the North and South Pole. And when the sun has a big event where it blows off many times more than normal charged particles, then there's enough that it's doing exactly what Gabriel said. The charged particles from the sun interact with molecules in the atmosphere. They excite electrons. Electrons fall back down to lower energy level, give off light that we see as aurora borealis. So we're seeing the same kind of light as you'd see from a neon gas tube. Yeah.
Is that the solar flare is?
Yeah. A solar flare is when the sun has a magnetic field line that essentially snaps, and you have huge amounts of energy released that blows off huge amounts of gas. All right. So, magnets. We talked about the magnetic field lines. The picture on the left is kind of fun, also very messy. You can take little iron filings. Iron is very strongly magnetic. You take those little filings and you pour them around a magnet, and the filings will form up and show us the magnetic field lines. So you can actually see what they look like there. And so it's very cool. Just like with electric field lines, the magnetic field lines are drawn so that the closer they are together, the stronger the magnetic field. So you can look at these and say, okay, closer here, farther here, so stronger where they're closer. How close are they inside of the metal here? They're really close. So what does that tell you about the magnetic field strength? It's very strong inside. Out here you can see it's much farther apart, so it's weaker. And the magnetic field lines always are coming out of north, going into south. All right. I've talked about everything here on this page except for the symbol we use for magnetic field is a B. It is a vector, so we have B with a line over it. Why does B stand for magnetic field? I don't know. When you study it more carefully, you also learn about M and H. But for general physics level, it's just B. What are the units of magnetic field? Without doing any derivation right now, the standard unit of magnetic field is the Tesla, named after Nikola Tesla. Right? Nikola Tesla was a genius, very clearly. And so he studied things with electricity and magnetism a lot. And it's for him that we named the unit. So later on, we'll learn what the fundamental breakdown of the unit Tesla is. But for right now, the standard unit for magnetic field is the Tesla. And of course, it should be a lowercase t because our unit names are lowercase, so we can distinguish the unit name from the person's name. We also have the Gauss. I think it's G for Gauss. The Gauss is not the standard unit, and in fact, 1 Tesla is equal to 10,000 Gauss. So it's just a unit based on the Tesla. The reason for that is then the Earth's magnetic field can be measured simply in Gauss. It's a half a Gauss, roughly speaking. So those are our units for magnetic field, which probably come up somewhere close. Notice this picture. It shows compasses, and the compasses are all nicely working the way they're supposed to. I bought a bunch of little compasses like this. And what I found is, through events similar to what I did here, after a while, it's like 50-50. It might point the right direction or the opposite direction. And so I don't bring them out that much anymore because it's more confusion than it's worth to say, yeah, this one's pointing the wrong direction, so it's just been reversed. What kind of confidence does that build? I can look and tell you which one's been reversed. I already talked about no magnetic monopoles. A key here, I mean, when I was in college, I had all these same ideas. I take a magnet, here's a bar magnet. One side's north, one side's south. Shouldn't I be able to snap it in half, and this side that says south will be the south, and this side that's north will be the north? But as you saw from those field lines, the field lines go through, and so if I break it in half, I still have those field lines going like this, and they'll still be going into the south and coming out of the north. So if I break it in half, I just have 2 smaller magnets. Break it in half again, they're smaller. I can never break it down to get to a single magnetic monopole because the smallest I can break it down to is to an atom, and that atom will have a magnetic north and south. I already said this. I said a lot of stuff in the beginning. I already said this. I already talked about the magnetic field and what makes the magnetic field. Good thing I talked about all this stuff. Let's see if we learned anything. Which magnetic pole is the Earth's north geographic pole? This one's going out long distance too. All right, we had 1 said north, 13 said south, 1 said both, 0 said neither, and 6 said it varies. Isaac. Hi. What you say, Isaac?
I said south.
Okay, why?
Because, well, from the picture, the Earth magnet, we'll just call it the Earth magnet, points south and north. So when you have a compass, the north is north-seeking, which means it's trying to find the opposite, which is south.
Perfect answer. Perfect answer. Okay. Now, when I said 6 people said it varies with time, there was a lot of, oh, why was that?
Because they're trying to basically, when the Earth puts its poles. They're like, well, it depends.
Yeah.
Another million years. Do it again.
Good. He sounds like me, doesn't he? Okay, so that was a perfect answer. So, I mean, people who said both north and south, if they meant it oscillates between north and south, that would be acceptable. It's not both north and south at the same time. So the time here varies with time. Those two are kind of combining the idea. Right now, if I'd said right now, then the only answer correct would have been B. So, good answer. Good, complete answer, Isaac. Thank you. Now talking about what causes magnetism and the types of magnetism. So one of the things that I find interesting in the history of science is, of course, we never know what we're talking about when we first start studying something. And so people noticed that electrons behaved like little bar magnets, that they had a magnetic dipole moment. And so they said, well, that makes sense because going to what I talked about, how the Earth makes its magnetic field, if I have conducting material like, charged electron, and it's going in a circle, that's going to make a magnetic field. And so it was hypothesized that electrons were essentially like tops, that they're spinning. And because they're spinning, they create a magnetic field. And so the magnetic dipole moment in an electron started to be called its spin. So we talk about the spin of an electron, you're just talking about its magnetic orientation. Pure and simple, that's what you're talking about. But here's the part that's funny. As people understood things better and started understanding the electron better, they started saying, okay, so what's the size of an electron? And through experiments, we can't say what the size of an electron is, but we can say for sure it's smaller than a certain size. I don't remember what that size is. But if it was spinning, it would have to be spinning so the surface was going well over the speed of light to create the magnetic moment of the electron. What does that tell you? It's not spin. Spin is not spinning. So when you talk about electron spin, you're using an anachronistic term, a term that they used to think had meaning, that we now know has no real meaning. What you should be talking about is just the magnetic moment of the electron. But because the theory started with them thinking it was spinning, we still stick with the terminology. Just like electromotive force, right? We know that we're not putting a force on electrons to push them through. We're making chemical reactions to give them energy, but we still talk about the EMF when we write that strict E with the battery. So the electrons have a magnetic moment. Protons and neutrons likewise have a magnetic moment. Of course, a neutron spinning wouldn't make a magnetic field in any case. And based on the magnetic moments of the nuclei, and in some cases the electrons, you end up with the magnetic properties of a specific material. And there are three fundamental types of magnetism. You have ferromagnetism. Ferromagnetism, everybody knows ferro is iron in Latin, right? So the symbol for iron is Fe. So ferromagnetism is magnetism like iron has. Iron's a good magnet. What's a better magnet than iron? Yeah. These nice little neodymium magnets are really strong. Somebody did me wrong here and took these apart. Let me, Randy, take those two apart. It's not an impossible task, but it's also not an easy one. Because they're super strong magnets. Now, the way you do it to take them apart is you have to slide them, right? You're never going to pull them apart. You have to slide them, and it's actually still pretty hard. But I just got to show you that it's possible. And so the way I try to keep these is by putting, this is 3 of them. I put the paper between them here so I can take them apart easily. There, that's how I like to keep them. Now, really cool things with magnets. I know I'm straying afield here, but this is cool. How many people like magic tricks? Okay, we all love magic tricks. Here's one of the classics. We're sitting at a little table, and I've got something here that looks like a fly or something. and I'm like, I'm gonna make it move. And I go, okay, so this is, that's bad position. This doesn't work, of course, because I don't have the right hand table. I go, and it's moving. And I go, right? All you need is strong magnets to make that trick work. It's pretty simple. There's some other really cool things though you can do, like set this down, bring the magnet down. Did you see what it did?
You picked it up.
It was more than picked it up. It flipped. How did it flip and pick it up? It's really strong is the first thing. And I had it on there so it was repelling. And so it's repelling, it's pushing away. If I'm not perfectly overhead, I'm going to have a little bit of a sideways. And it's that sideways that's the key that makes it pull the bottom up while it's pushing the top away, doing the flip because I'm not directly over it. Cool things with magnets, right? Yeah. I mean, why else do we go with physics? Let's play with things. You guys have figured that out, right? Because it's fun. So, this here, which I believe is neodymium, makes an even stronger magnet. So iron is well known, other things, nickel, cobalt, chromium dioxide. Anybody here ever had a cassette tape, audio tape?
Oh, yeah.
Thank you. Just this week, I paid somebody $16 to transfer to cassette tapes to CD, because, CDs will last at least 20 years without degradation, whereas the cassette will last 5 years without degradation. This is interviews with my grandma, so it's actually more like 30-year-old tape. So I wanted to get them transferred while there was still something you could hear on it. But what they do with those tapes is they put a gel on top of your cellophane. So you have cellophane, they put a gel on it. And inside that gel, they put little magnetic pieces. So if you look at those, some of them will say like, cobalt 2 or cobalt or chromium 2 or chromium 3. And I used to look at those when I was a kid. I'm like, I don't know. I don't know what that means. I don't know if it's better or if it's worse. Those were telling us what kinds of material they stuck in the gel. And then in that tape, you pass it over a little thing that has a magnetic field that will change orientation. And those little magnetic domains will align just like when I talked about the magma coming out of the Earth and freezing parallel to the Earth's magnetic field. And so that tape was simply storing different orientations of these magnetic domains. And then you go by and you read the magnetic field directions, and that's how you read a cassette tape. It is not ancient technology. If you have a hard drive in your computer, it's doing exactly the same thing. The only difference is instead of a cellophane tape, you have an aluminum platen. And on top of that platen is the gel, and then you have the little magnetic materials in the gel on top of that. So it's still very useful. Going off base, we got some computer science people here. You ever experienced a core dump? No? Oh my goodness, what do they teach you anymore? When I was in high school and college, you would have the computer crash, and instead of that whole blue screen of death, it would just say core dump, and you would see a number counting up really quickly, and then it would shut down. And that core dump is reading the memory state of all of your RAM and storing it to the hard drive, and then shutting down. And the reason it's called a core dump is the first memory in computers was with magnetic cores. They took pieces of iron and they put them in a strong magnetic field like this. And you could either make a strong magnetic field that points up or one that points down. And they align with that, and then you come and you check and you see which direction the magnetic field is pointing to read the memory. And so the core dump was measuring the orientations of each of the magnetic cores and storing that. I can't believe you guys don't know what a core dump is. That makes me sad. Yes?
So does a solid state drive work the same way with the...
No, a solid state drive is working with transistors. And much faster. Okay, so different types of magnetism besides ferromagnetic. There are three types. Ferromagnetic means strong magnetic. And ferromagnetic has the attraction repulsion we're used to. if I take a ferromagnetic material like iron and I bring it close to a magnet, whether my ferromagnetic material is itself a magnet or not, it's always going to be attracted because it has the magnetic dipoles, just like electric dipoles. It will rotate, so the side it's attracted is closer, it's pulled in. Diamagnetism is present in all materials. And diamagnetism is diametrically opposed magnetism. So magnetism is attractive, right? That's actually the root of the word. Diamagnetism is a repulsive magnetism. And everything has diamagnetism. So how is it that I can make things attractive that have diamagnetism? Because if it's ferromagnetic, it has strong magnetism. The strong magnetism is far, far stronger than the very weak diamagnetism. But if we take something that's not ferromagnetic and only has diamagnetism, we can do cool, stinking things, like levitating that frog. You can go on YouTube and you can watch the video. I do. I have it queued up. That green link is the link to it. I don't have it queued up, and it would take me half the class period to get it queued up. But you can watch the video of the frog there just levitating in a magnetic field, which is totally cool. And as far as they can tell, it doesn't do any damage to the frog whatsoever. How can they levitate this frog in the magnetic field? First of all, the frog is largely water, just like you and me, which means they can do this to you and me as well. Because it's largely water, and water is diamagnetic, the water is weakly repelled by a magnetic field. So you just make a really strong magnetic field down here, you put the frog above it, and it's weakly repelled and it floats. It's totally cool. I mean, it's physics, right? I've said totally cool like, 20 times today. So that's what diamagnetism is. And then we have paramagnetism, the one on top here. Paramagnetism, I suppose, is like a paramedic. They're kind of like a medic, but not all the way. I was an EMT. That's kind of like a paramedic, but not all the way. There's levels, right? I was the lowest. So paramagnetism is attractive like ferromagnetism, but it's very weak. And so every material is diamagnetic. If it's paramagnetic, the paramagnetism is going to be stronger than the diamagnetism. If it's ferromagnetic, that's way stronger. So, I want to get to pictures. This word domain is what I want to get to. There's a pretty picture to go with it. Here's the pretty picture. Here's what's going on in something like my bar magnet here. In the bar magnet, it by default has a bunch of little magnetic domains, a bunch of regions where the atoms are working together in their magnetic orientation. And by and large, those regions are randomly oriented. So it's not a magnet, generally speaking. This is because it's been oriented. But generally, they're not magnets. But they have a bunch of little magnetic regions that are just randomly oriented. But then when you take it and you bring it close to a magnet, this is not a magnet. Bring it close to a magnet, and it does stick to it because those little domains will align with it. If I take it away, they didn't stay aligned. They kind of rotate a little. I take this away, and they rotate back to where they were. If I raise this metal up to the Curie temperature, or this metal, the Curie temperature, it's about 778 iron, is the temperature where the magnetic domains are free to rotate. It's below the melting temperature. But if I raise it up to the Curie temperature, they will all just become free to rotate. If I put in a magnetic field, what will they do? They'll all align with it. Then if I freeze it while it's in the presence of a magnetic field, I will make a strong permanent magnet. Permanent unless I do something like put in a really strong magnetic field that creates enough torque to make them rotate. So that's what I was doing with this. This material here is called magnetically soft. That means the magnetic domains can rotate to some extent. So if I put in a really strong magnetic field, they will rotate. And that's how I can make this a stronger magnet by sticking it in here, put the strong magnetic field through it, and I just made it so it's much stronger than it was a minute ago, well, a few seconds ago, by aligning the magnetic domains. Now, those domains are not perfectly defined. Atoms can defect from one domain to another, so they can grow and shrink. And so in this picture, you see the domains grew. But that's how we actually get ferromagnetism, which is totally cool. Here's where it talks about the Curie temperature. And soft iron here. Electromagnets. Electromagnets, and I will later bring out my ring tosser demonstration, which is totally cool, like everything else I'm talking about today. And when you have a magnetic material with these little magnetic domains, when you put in a magnetic field, those domains align and make the total magnetic field stronger than just the external magnetic field. And in fact, in something like iron, it'll make it somewhere around 700 to 1,000 times stronger. So by putting a magnetic core inside of a coil that's making a magnetic field, we'll talk about why later. By putting a core inside of a coil, I can increase the strength of the magnetic field by like 1,000 times. So of course, anytime you're trying to make a strong magnetic field, that's what you do. You make a coil to make a magnetic field, and then you put an iron core in it to amplify it. So it's another really cool thing about magnetism. If nothing else today, you'll have learned what's totally cool. Hey, look, here's an application. Uh-oh, it's a platter. I thought it was a platen. RN platter. Platter, I guess, makes sense. Flat disk. So I've already talked about how the hard drive works. And I'm going to end with just 3 clicker questions. Just 3. Number 1, which kind of magnetism is always present in materials? Okay, everybody has answered. And okay, that's a reasonable, I'm not going to call on somebody here to answer. That's a reasonable distribution. The correct answer is the majority. Diamagnetism is always present. How do people get confused with paramagnetism? Well, you know it's not ferromagnetism. Ferromagnetism is the strong one. Not everything is strongly magnetic. Take, for instance, okay, so here's my strong magnets. I can bring these strong magnets. I think that's metal. I know that's metal. Not attracted at all. Right? That just means it's not magnetic material. So not all metals are magnet. Not all materials are magnet. Clearly my magnets are not attracted to this. They're not attracted to the plastic, or I wouldn't be able to easily take them off the plastic. So paramagnetism is a weak attraction. Ferromagnetism is a strong. Oops. Which kind is strong? Guess you're all going to get this one right. What? Wait, you were talking? People were answering before you could read the question. Excellent. We had a student last semester who was constantly doing that. Or was it last semester? I don't know. Okay, so this time everybody was correct. Last question. Did them both this time. Which kind of magnetism is always repulsive? Okay. And this time we had 13 and 8. Gabriel, can you explain to people why your answer is correct?
So I went with paramagnetism because the other 2 were already correct. Diamagnetism isn't inherently repulsive, and neither is ferromagnetism, so it's a process of elimination.
Okay, the correct answer here was the majority answer. It was diamagnetism. Remember, I used the words diametrically opposed. The dia means opposite. So diamagnetism is repulsive, which was also the answer here for always present.